Okay, guys, so in this lecture, we're going to be talking about complex numbers. So, we'll start off this complex numbers lecture with a useful thought. So, I'm going to start with a useful thought. And that means we can pass between Cartesian and polar coordinates. So if z is a complex number in the form a plus bi, has modulus of z equal to some r, and the argument of z is some angle theta, then, well, if I draw a quick diagram just to illustrate what's going on, I have my complex number represented by some r and some arguments theta, such that I can break this apart as r sine theta, using a little bit of trigonometry, and r cos theta for that bit there. So from this, we can say, well, the a bit, the real part, is equal to r cos theta. And the b would be equal to r sine theta. Because this here is my real axis, this up here is my imaginary axis. I.e., from this point here, we have z can be rewritten in the form r times cos theta plus I sine theta. And that is the modulus argument form of a complex number. We also know if z is a plus bi, then we can say, well, then we know that r is the modulus of z, which by definition is just the square root of a squared plus b squared, and tan theta, using a little bit of trigonometry, will be just b divided by a. Essentially, r sine theta divided by r cos theta. That's what I'm going on about there. Okay, of course, I want to make sure if a isn't 0. I am very careful when dividing by 0, and I will also write down here that determining theta is quite delicate. So you just need to be careful that your theta is between minus pi and pi radians, because all these complex numbers will be in radians. I will be never using degrees unless I specify so. Okay, so we're on to our next proposition, which is proposition 5. So proposition 5, if I remember what proposition 5 is, we take z and w in the complex plane, but we exclude 0, but not 0. Then we have that the argument of zw is the same as the argument of z plus the argument of w. And this, if I make a note of on the side here, that this looks like log. Because we have a log law that links the log of xy is log x plus log y. It's not a coincidence that this looks similar like a log law. It's not a coincidence whatsoever. Alright. Let's keep going. We do need to be careful that we are here will state that we are working with argument modulo 2 pi. Because if you're not working with 2 pi, well, this will work, but I don't like to use it too much otherwise. So let's prove this thing. Proof. The proof is actually quite straightforward. We let theta to end up being arg z. And we will pick another Greek letter. We'll pick phi. Make sure you do learn your Greek alphabet to be the argument of w, such that then we can write z as the modulus of z times cos theta I sine theta, and we can write w as the modulus of w of cos phi I sine phi. There we go. Okay, so we've set up our complex numbers in mod argument form. Then we actually need to prove this thing, so we need to find ZW. I mean, that's not too bad in terms of work. We've got mod Z, mod W. You can multiply the moduli, and then you can go, so you get cos theta cos phi minus sine theta sine phi, times by cos theta sine phi plus sine theta cosine of phi. Close my bracket. So, this, if you think back to your trig work that you did in LMAS, or whichever equivalent you did, that these look like your double angle formulae. So, you would end up having cos theta plus phi plus I sine of theta plus phi. So, the argument of ZW is theta plus phi. And that will end the proof. So, the proof isn't too bad here for this proposition. I just make sure that you're aware of this proof because we will be coming at it again in a few lectures' time, so just make sure you're aware of it. Okay? So, because of this, we can make a remark. Remark. We can interpret multiplication in the complex plane in C geometrically. I multiplying by z as a complex number, but not 0. Rotate the complex plane anti-clockwise by the argument of z and enlarges by factor mod z. I will say at the origin. Okay, nice little remark there. So we're on to a definition. I will also underline what I'm defining as well. So the unit circle, which is what I'm underlining, in C, so in the complex plane, is S1, which is Z is a complex number such that, that the modulus of Z is equal to 1. So really the only thing that's new here is that the unit circle can be represented by S1. The remark here, we can say, well, we've just seen that S1 is equal to, well, it'll be cos theta plus I sine theta from what we did before, such that theta is belonging to the real numbers. For Z in S1, we have Z minus 1 is equal to Z bar in S1. Z bar here is the complex conjugate. Now, we met the complex conjugate in our last lecture, and it's also worth noting something that you will do later on in your degree is such that S1 is a group under multiplication. This is something you come up way later in your degree, but it's worth pointing out now, basically, so A, I don't forget it myself, and B, if I don't mention it now, I will forget. So it's just a pointer for me to make sure I mention that. And yeah, I have underlined what the bit I'm actually saying about S1 is. So it's an S and a little 1 and like a power sort of thing. That will basically just mean the unit circle. So if you write Z a little exists S1, then I know what you're talking about when you're writing your solutions up for me. Okay, I will send you this as well as I post this. I'll put a link to it and you can download it. If you don't want to read it while I'm doing it, it's up to you. And you might want to put it on a faster speed as well, because I do talk a little bit slowly, so as I'm explaining, of course. Okay, so excitingly, we've got a new theorem. Our next theorem will be theorem 6. And this theorem is something called de Moivre's theorem. Or de Moivre's theorem, as some people like to call it. But I go with the proper French de Moivre's theorem, of course. So, we say, for z in S1 and n in Z, we have what do we have? The argument of z to the n is n times the argument of z. And again, this looks like a logarithm. We know if we've got log of x to the y, we can bring that y down to the front. Again, this looks like a logarithm. It is not a coincidence that this looks like a logarithmic. And, more importantly, equivalently, now if you've done L Fermat, you'll recognise this form I'm talking about. You won't recognise the first one, but you will recognise this one. We have for theta in R, and we have n being a complex number, we have the cos theta plus I sin theta to the power of n is cos n theta I sin n theta. This is the form you probably recognise from your A-level studies. Again, we don't use this one too much at university level. We do use the argument of z to the n is n times the argument of z quite a lot. It's just something to be aware of, really. And sometimes you don't have to always state that you're using de Moivre's theorem all the time. But again, you're totally allowed to. It's up to you. Right, now let's prove this thing. Proof. We fix z in S1. So for n being positive, for positive n, we use induction on n. This is proof by induction here, by the way. So if n is 0, the base case, we have z to the nothing being equal to 1. So the argument of z to the 0 is 0 n times the argument z. That's just a quick check. Again, this is the easy part. The next part is where we actually do some work in the inductive step. Suppose that the result holds for some positive n. So the argument z to the n is n times the argument of z. Then the argument of z to the n plus 1 is the argument of z to the n plus the argument of z by proposition 5. I'm not going to write down every time I use proposition 5 because you use it a lot. But for this one time, I will write down that I'm using proposition 5. Okay, so we're up to this point. We've assumed it's true. Well, here, if we're assuming this is true, then this is n times the argument of z plus the argument of z by the inductive hypothesis. So the result holds for n plus 1. And again, you don't need a long conclusion here. At university level, we don't use long conclusions because we assume this is stuff that you should already know. Okay. So for negative n, then, this is the new bit. We're going to use the result for positive n. So if we use the result for positive n, we fix n to be less than 0, and we let m to be minus n, i.e. so m is positive, not less than 0, sorry. I will correct that. So that m is positive. Now the argument of w to the power of m is m times the argument of w for any w lying in S1, and z to the power of n we know is z minus 1 to the power of m, which we know is z bar to the power of m, and the argument of z bar is minus the argument of z, so the argument of z to the n is equal to the argument of z bar to the power of m, which is m times the argument of z bar, which is m times minus the argument of z, which we know is n times the argument of z. And that ends the proof. Whoa. Okay, so the proof is not easy here. I will say that. The proof is not straightforward. But hopefully now, this lecture is sort of explaining why it is the way we're doing it. Excitingly, I have an example for you. And the example of where this is quite useful, so this is the last thing we'll do for now. The example is the trig compound angle formulae. So, par exemple, And for theta in R, we end up having cos 3 theta plus I sine 3 theta plus I sine theta cubed as a power of 3. Right. Now, I'm not the brilliant at expanding out cubes, but we'll give it a go. So we have cos cubed theta minus three cos theta sine squared theta plus I times by 3 cos squared theta sine theta minus sine cubed theta times by I. So, if we wanted some formulae, we could comparing real and imaginary parts, we get the cos 3 theta being cos cubed theta minus 3 cos theta sine squared theta. And at this point here, you can tidy this up a little bit better than probably I can. Minus 3 cos theta, lots of 1 minus cos squared theta. Tidying that up, we got 4 cos cubed theta minus 3 cos theta. And you can do the same for sine of 3 theta as well, if you wanted to. So you got what? 3 cos squared theta sine theta minus sine cubed theta. So we just need to replace the cos squared there. So you get 3 sine theta, won't you? You get the minus 4 sine cubed theta. Okay, so at this point here, I'm going to make a short pause and let you copy all that down. In the next lecture, we're going to explore nth roots of unity excitingly. Nth roots of unity, I consider one of the hardest things that you do with complex numbers. So we'll go through some notes for that. For the time being, I will leave these notes with you, and thank you very much for watching.